So it's my pleasure to Allen Schirm and Ron Wasserstein. Allen is retired from Mathematica policy research. He got his PhD in economics from the University of Pennsylvania after getting his bachelor's degree in statistics at Princeton University. He's been retired for a short time now. Ron got his PhD in statistics from Kansas State University, and Ron is a native Kansan, just like our morning plenary speaker, Jane Watson, is. And Ron went on to work at Washburn University in Topeka, Kansas for many years, eventually achieving the role of Vice President of Academic Affairs at Washburn. For the last 12 years, Ron has been Executive Director of the American Statistical Association. And as you know, if you were at last night's opening session, the reason that I invited Allen and Ron is because they were two of the three editors of the recent special issue of the American Statistician that takes on the challenge of thinking about statistical inference for the 21st century. They, along with Nicole Lazar, were the three editors and also the writers of the lead editorial that's gotten a lot of good publicity from Nature magazine and other places and has over 80,000 hits on the ASA webpage already. So they're here to talk about what their recommendations are, what the association's recommendations are with regard to statistical inference in the 21st century. So thanks very much for coming. We look forward to your presentation.
Thanks, Alan.
This is a P-Values update with your hosts, Allen Schirm and Ron Wasserstein.
Good afternoon. I'm Allen Schirm.
And I'm Ron Wasserstein. If you're a parent, then you know what the talk is. Of course, I'm referring to that discussion that you have to have sooner or later with your young'uns about human reproduction, the birds and the bees. I have no idea where that metaphor comes from, since that's about as far from human reproduction as you can get. About 5 years ago now, my wife and I brought home two boys from Haiti. And about 3 months after they joined our family, I was minding my own business down in the basement watching a baseball game, and I have no idea what the discussion was upstairs that made my wife realize that the boys needed to come down and have a talk with Dad about human reproduction. But downstairs they came, and this talk is difficult enough, but it's even more difficult when you have two boys who speak very little English and a dad who speaks no Haitian Creole. Well, I mention this because in the 3 years since the ASA Statement on P-Values was released, I've had the opportunity to talk to a lot of people about P-Values, and I've come to realize that these two discussions, the one about P-values and the talk with youngsters about human reproduction, have a lot of things in common. Let me illustrate. They think they know all about it already because they've learned about it from their peers. It turns out that the discussion is not nearly as interesting as they thought it would be. They stopped listening long before I stopped talking. And this is just a warning about the rest of this presentation. Chances are they understood it even less than when it began.
Thanks for the talk, Ron. Though we're all statisticians here, perhaps it'd be good to clarify what a p-value actually is. The ASA Statement on P-Values and Statistical Significance, which we'll be talking a lot more about in a few minutes, informally defined a p-value this way. Informally, a p-value is a probability under a specified statistical model that a statistical summary of the data, for example, the sample mean difference between two compared groups, would be equal to or more extreme than its observed value. Christy Ashwanden, who at the time was with 538, didn't think much of that definition, calling it clear as mud. Well, perhaps this is clearer.
Just to make sure that we're all on the same page about p-values, I know we're all together as a bunch of statisticians, but let's just walk through what a p-value is. Sorry, went the wrong way there. All right. So we know some stuff. We're trying to learn some things, so we want to know a few more things. So we design an experiment to help us. We collect some data from the experiment. And now we're going to summarize the results and then figure out what more we know as a result of that. So let's focus in on that data summary part a bit. We summarize the data into a number that we call a statistic. And then we compute a probability from that statistic, and that's what we call the p-value. And if the p-value is small enough, we call that statistically significant. And what is small enough? Well, over history, that number has typically been 0.05. So here's a numerical example from an article in the Public Library of Science. There was a new treatment that's being compared to a placebo to improve a measure of health in kidney patients, TKV, that's total kidney volume. And if you want to ask me any questions about total kidney volume, you're going to be very disappointed in my knowledge about that. But 1 year after patients had been receiving this treatment, the difference in median total kidney volume, that's treatment minus placebo, was 96.8 milliliters, and there's the 95% confidence interval that they measured, and the p-value rounded off was computed to be 0.03. So let's focus in on that 0.03 here for a moment. How do we get that number? Well, to compute a p-value, you have to assume a bunch of stuff, and one of the assumptions that you have to make is that there's no difference between the treatment and the placebo. So what does our p-value tell us? What does it mean? If there's no difference between treatment and placebo, and if everything else we assumed is also true, then the probability that we would observe the difference that we observed, that is that 96.8 milliliters of TKV, or one even larger, was about 0.03. Now, what can we conclude? Well, technically what we're concluding with the p-value is a measure of model incompatibility, but let's say that in a little bit simpler terms, that we really had either some bad luck in our sample selection, or that one or more of our model assumptions was wrong. And remember that one of those assumptions was that the treatment was no better than the placebo. Okay? So our p-value was 0.03, and guess what? That's smaller than 0.05. And so that's statistically significant.
Thanks, Ron. Speaking of statistical significance, the ASA has had some concerns about that, and so does our special guest commentator, Emily Latella. Emily.
What's this I hear about you people trying to ban statistical significance? Why, I think that what people do in the privacy of their own homes is none of your cotton-picking business. If it happens to be statistical and the adults involved don't mind, well then who are you to say? Why, in my day, you could be statistical even if it wasn't significant.
Emily.
What?
Statistical. Statistical significance. Not sadistical. Statistical.
Oh, well, never mind.
That's Emily Latella, played by Roxy Peck. Thanks, Roxy. Well, when R.A. Fisher introduced the term statistical significance, he didn't have a lofty meaning for the term. He meant that the results were worthy of further scrutiny. But if you think that significant doesn't have weight, just consider these opposites. Insignificant, unimportant, meaningless. Now think of using significant as an adjective. We like receiving significant increases. We have significant events in our lives. Our co-author, Nicole Lazar, is not here with us because her son's bar mitzvah is tomorrow. That's a highly significant event. We refer to people close to us as significant others. But you'd get in a lot of trouble if you told your partner, honey, the data shows you are, well, nearly significant to me.
That's a good point, Alan. Think about this word, mole. What's the first thing that comes to your mind? Maybe it's this furry little creature here that digs up holes in your backyard. Maybe it's a particularly well-placed spy. Or perhaps for some of you, it's a scientific unit of measurement. But chances are you don't get mixed up between the various uses of that word. But here to tell us about some very misused words in science is none other than the founder of this conference. Ladies and gentlemen, it's Alan Rossman.
Hey, Ron. Hey, Alan.
Hey.
A few years ago, Scientific American wrote a very interesting article, Just a Theory, 7 Misused Scientific Words. The top word on the list is hypothesis, a word we use a lot in statistics. In the article, they say, the general public so widely misuses the words hypothesis, theory, and law that scientists should stop using these terms. A hypothesis is a proposed explanation for something that can actually be tested. But if you just ask people what a hypothesis is, they just immediately say it's an educated guess. Similarly, people dismiss things as just a theory, when in fact a scientific theory is an explanation of some aspect of the natural world that has been substantiated through repeated experiments or testing.
Alan, what are some other words on that list?
Skeptic is another word that has lost its right meaning. True skeptics are open to scientific evidence, even willing to evenly assess it. Nowadays, the word skeptic tends to be associated with people who refuse to listen to evidence or tend to flatly deny facts.
So, Alan, that's interesting, but what does that have to do with p-values?
So now you're a skeptic. Word number 6 on the list of misused words is significant. This is not surprising given what you mentioned earlier. This is why I suppose that you commented in your editorial that Fisher's idea has been irretrievably lost.
That's correct, Alan. Thanks. Alan Rossman, everybody. Let's take a look at the problem with how significance is misused using a slightly different example. Let's take a look at our 0.03 p-value as though it was a Tinder date. Okay? So Fisher meant 0.03, meant statistically significant, sort of like a right swipe in Tinder. It means that you are expressing some interest. A right swipe in Tinder and a statistically significant result is sort of like this. It's the idea that your experimental result is interesting. Maybe something that you want to investigate a little bit further. That's what statistically significant is supposed to mean. It's not this. The idea behind statistical significance is that you're expressing interest. It's not that you're ready to book the wedding venue already.
Now, you might be thinking we're exaggerating a bit about the effects of dichotomizing p-values into significant or not significant. But here are some examples from the literature. These are things that people have actually published, trying to explain their p-values when p came out to about 0.06. Almost significant. Almost attained significance. Almost significant tendency. Almost became significant. Almost, but not quite significant. Almost statistically significant. Almost reached statistical significance. Just see that p-value. Just barely below the level of significance and just beyond significance.
Now, remember, these things are written by human beings. People just like you and me. But they had a problem. The problem they had is a p-value that didn't cooperate. It didn't get down to the 0.05 level of significance. And these people that I'm about to show you now have a bigger problem than those people Alan just showed you. Their p-value was more recalcitrant. It was 0.08 rather than 0.06, and so they had more problems to work with. A certain trend toward significance, a definite trend, a slight tendency toward significance, a strong trend toward significance. Do you see a trend in these answers here? Now, I'm going to stop here to ask a question of the crowd. I'll start over on this side, and as I work around here, I'm just going to ask you to think about how many numbers it takes in your mind for a trend to develop. So over here, you can think about this. How many does it take for a trend? Maybe towards the back, you can think how many it takes to develop a trend in your mind. And over here, how many it takes for a trend. And there may be differences in what you think versus what you think versus what you think. But I'm going to guess that whatever number it takes to develop a trend, that number is more than 1. A trend close to significance, an expected trend. Those are the best kind of trend. Approaching our criteria of significance, approaching borderline significance, which sounds much more like a condition than anything else. Approaching, although not reaching significance.
And here's the worst case scenario. These poor folks got p-values that were close to 0.05, but didn't get quite below that threshold. Now this is when it really does get statistical. Hovered at nearly a significant level. I don't know, maybe this is getting back to the birds and the bees hovering, or helicopters or hummingbirds, or I don't know. But another hovers on the brink of significance. Just about significant, just above the margin of significance. So now we have a brink and we have a margin. Just at the conventional level of significance, although it took 5 decimal places to show that it wasn't below 0.05. Just barely statistically significant. Just borderline significant. So we have brinks, margins, and borderlines. Just escaped significance. You can see that p-value running down the street. And just failed significance.
We only wish to emphasize that dichotomous significance testing has no ontological basis. That is no reason for being. That is, we wish to underscore that surely God loves the 0.06 nearly as much as the 0.05. Rosnow and Rosenthal go on to say in that same article, can there be any doubt that God views the strength of evidence for and against the null as a fairly continuous function of the value of p?
Well, thanks to Matthew Hankins for these quotes, and you can find these and more on his website. So, why did the ASA decide to write a statement about p-values and statistical significance? Well, certainly the problem was well known for decades. It has been widely felt, probably for 30 years and more, that significance tests are overemphasized and often misused, and that more emphasis should be put on estimation and prediction. But this point was made by David Cox 30 years before the ASA statement, and he refers to 30 years before that, meaning that basically these problems of p-values and statistical significance have been going on for more than the entire lifetimes of Ron and me. Now, there are many more quotes just like this one that you can find scattered in the literature over the years. David Parkhurst has collected quite a number of them, and they can be found on his website. Well, this is why in their introduction to the ASA statement, Ron and Nicole acknowledged that nothing in the ASA statement was really new, though that's not entirely true. What was new was that the ASA decided to tackle the issue. Why did it decide to do so? because articles like these in Science News began to appear. Odds are it's wrong. Science fails to face the shortcomings of statistics. And p-value ban, small step for a journal, giant leap for science. Now, the second headline prompts me to make a small historical correction for the record. The ASA board authorized the project that led to the ASA statement on p-values and statistical significance before the Journal of Basic and Applied Social Psychology banned p-values, just for the record. Anyway, Tom Siegfried, in that article you see on the left, wrote these words. During the past century, a mutant form of math has deflected science's heart from the modes of calculation that had long served so faithfully. Science was seduced by statistics, the math rooted in the same principles that guarantee profits for Las Vegas casinos. Supposedly, the proper use of statistics makes relying on scientific results a safe bet. But in practice, widespread misuse of statistical methods makes science more like a crapshoot. I think my colleague Ron here might have read those words and gotten just, a little p-valued off.
That's true. The ASA statement has gotten a lot of reaction. We've received more than 310,000 downloads of the statement, and it's been cited over 1,800 times.
Well, Ron, is that a lot? You know, as statisticians, we need a basis for comparison. You know, how about we compare it to, I don't know, maybe this Ron Wasserstein authored article with, what is that, 17 views?
Oh, well, okay, so that's a lot compared to that article, yeah. And it's not a lot compared to, say, 2.6 billion views of Taylor Swift's Shake It Off video. And it's not a lot compared to 13.3 million views of last week tonight episode of John Oliver's episode on scientific reproducibility, which, by the way, I highly recommend if you haven't seen that. You can't show it in your classroom because it's loaded with the F-bomb. You might be able to assign it as something that could be seen. But let me just say parenthetically, it's really worth watching. It's very well done. And one of the things that it highlights in there is this paper that is highlighted here with this Chiron glass of red wine equivalent to hour of gym time. So the actual work that's done in this paper is quite legit. The actual story itself, the actual research itself is about a specific group of people whose very limited physical capabilities are such that for them, a glass of red wine does produce effects that are equivalent for them to an hour of gym time because they are not capable physically of having an hour of gym time. But by the time it got all the way to a certain network there, it became a glass of red wine equivalent to an hour of gym time. The headline really should read, "Groundbreaking new study finds that new studies rarely break any new ground."
Well, I still enjoyed that second glass of red wine last night, in any case. So, the ASA statement articulated 6 principles. But for our purposes today, we're going to focus on just 3 of them. Number 3, scientific conclusions and business or policy decisions should not be based only on whether a p-value passes a specific threshold. Number 4, proper inference requires full reporting and transparency. And number 6, by itself, a p-value does not provide a good measure of evidence regarding a model or hypothesis. But probably the biggest message of the ASA statement is that bright line thinking has been bad for science. This is vividly expressed in this quotation from Ken Rothman in his supplement to the ASA statement. Scientists have embraced and even avidly pursued meaningless differences solely because they are statistically significant, and have ignored important effects because they failed to pass the screen of statistical significance. It is a safe bet that people have suffered or died because scientists and editors, regulators, journalists, and others have used significance tests to interpret results and have consequently failed to identify the most beneficial courses of action.
The ASA Statement was developed over an 18-month period by a diverse panel of about 30 experts. The statement did not go as far as it needed to, in that it gave more advice about what not to do, but not about what to do. But it went about as far as experts could agree on. And in that it was a statement that reflects the state of the profession, it is powerful. Again, it declares that decisions should not be made only on the basis of bright lines. It demands full reporting and transparency. It recognizes that 0.05 is not a very strong place to set the line, and so on. It's pretty hard to ignore.
Nonetheless, it immediately ran into what's really fair criticism. What do you want us to do? That's why phase 2 of what the ASA refers to as the P-Values project was a symposium on statistical inference, held about 19 months later in Bethesda, Maryland. Speakers were challenged to focus on what could, quoting from the original proposal to form the symposium, drive change on the matters raised in the statement, providing necessary impetus for lasting improvements in science and society in the teaching of statistics, statistical practice, and the dissemination and many uses of statistical results. Well, those are lofty goals, so while we were at it, we wanted to solve the problems, maybe on the Korean Peninsula, slow the pace of global warming, and make a Nickelback record go platinum. Alas, certain problems remain intractable.
Following 3 great days of presentations at the symposium, we opened up the discussion to the world. We issued a call for papers for the American Statistician, open not only to symposium presenters, but to everyone. The key is that we wanted people to write for the non-statistical audience, and we wanted to be able to give that audience advice about how to move beyond P less than 0.05. So here's a quick review of the abbreviated timeline for this. George Cobb challenged us to take on the P-Values issue in February of 2014. So we had a lot of discussions between that time with that P-Values panel I showed you earlier until we finally met in October of 2015. In March of 2016, we published the P-Value Statement. We held that symposium we mentioned in October of 2017, and the next month we issued a call for papers. Now, we hoped foolishly that we would publish the special issue in July of 2018. Then we pushed that deadline back to October of 2018, then December of 2018, and we finally published in March of 2019. But to be fair, we had no idea that we would receive 100 papers and ultimately publish 43, which is the equivalent of 3 regular issues of the American Statistician. We were able to accomplish this because we had a fantastic set of associate editors who took on these papers and often had to look at the same paper multiple times because of multiple reviews. And of course, all of you have ever been associated with publishing a journal or doing any sort of submission of papers knows that you have to have a great set of reviewers and that these reviewers have to remain anonymous. So we thank all of the anonymous reviewers that we had working on these papers.
Well, the significant development in the editorial that introduces the special issue is our recommendation to say farewell to the use of the term statistically significant and all of its various cousins. Ron, Nicole, and I argue this for several reasons in the editorial. We've already mentioned today that the original intent of statistical significance has long ago been lost. We've illustrated that having bright line rules for declaring results significant or not significant leads to bizarre behavior. It's well known that such bright lines drive people to p-hack their way to results, or to leave behind results that might otherwise be interesting, what Rosenthal called the file drawer problem. More to the point, though, is we know from decades of complaining about the ill effects of misuse of p-values and statistical significance that complaining doesn't do any good. In fact, in this optimistically titled article in the special issue of the American Statistician, Ray Hubbard shows that even with highly cited articles over several decades decrying the use of null hypothesis significance testing, its prevalence increased throughout the period.
We argue in our editorial that it's time to move on. If you really understand p-values, there's no important information added to the p-value by slapping a label of significance on it. In fact, it is our view, and we don't think we're anywhere near the first people to think this, that statistical significance has allowed many people to escape the hard work of thinking about what their p-values are actually telling them. We felt this sentence from section 2 of our editorial was really important. And if we'd known it was going to be so easily overlooked, we'd have used boldface, a different font, or at least followed with some mad tweet storms about it. We believe that a reasonable prerequisite for reporting any p-value is the ability to interpret it appropriately. By this, we're careful to say in the editorial, we are not encouraging a special format by which individuals mindlessly write sentences from some template like, if all the assumptions hold, then the probability that I would observe the test statistic I observed or a greater one, blah, 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 blah. Nope, that's not what we're talking about. Please take a look at the editorial for more details. Because you, statistic educators, know how hard it is to avoid all the common mistakes. Recalling that 0.03 p-value that I showed you in the earlier example, you know that you'll get these kinds of misinterpretations. There's only a 3% chance that the placebo was better than the treatment. There's only 3% chance of getting the result that we did by chance alone. The probability that the null hypothesis is false is 97%, and so on. And part of the reason these misinterpretations are so common is because these are the probabilities that we'd really like to get from the p-value, but we can't. And we haven't had time to discuss the fact that perhaps the subtlest problem with significance testing is that we really don't reject the null hypothesis. What we're finding is that our model is not compatible with the data. Whatever our model is, it includes the null hypothesis, but it also includes all of the other assumptions. But once statistical significance is declared, how often do you see anyone worried about all those other assumptions? And what are those other assumptions? Every choice that was made from design to conclusion, from design to the final calculation of the statistic, everything that someone would have to know to reproduce the statistic from the raw data, each of those choices affects the p-value. We know that the things that we're talking about raise really hard issues for statistics educators, and that's why we're really grateful to have the opportunity to talk to you today, and we're especially grateful that this conference is taking on this topic. We need your help to move to a world beyond P less than 0.05. In that world, what do you have to do to get your paper published, your research grant funded, your drug approved, or your business or policy recommended approved? We think this requires some serious change at the atomic level.
That's right, Ron, but what does that mean? As we looked at the recommendations of the 43 sets of authors in the special issue, we summarized the recommendations in 4 categories. To move beyond dichotomized thinking, requires that we accept uncertainty and be thoughtful, open, and modest. Accept uncertainty. That's what statistics is all about. That's what we're all about. But it's much harder to bring non-statisticians into that way of thinking. We have to go back to first principles in encouraging full reporting of descriptive statistics, including estimates of variation as well as location. But what we're talking about goes back much further than the description of the data. It goes to the collection of the data, to the design of experiments, thinking about all of the sources of uncertainty. Of course, there's nothing really new there. As to the rest of the Adam mnemonic, let's be clear that Ron, Nicole, and I don't think that researchers are thoughtless, narrow-minded, and egotistical. Though, every one of us might display one or more of those characteristics from time to time. Rather, in the editorial, we encourage some specific ways to be more thoughtful, open, and modest in our approach to research. For example, thoughtful research looks ahead to prospective outcomes in the context of theory and prior evidence. What magnitudes of differences, odds ratios, or other effect sizes are practically important in the substantive context? Thoughtful research considers related prior evidence, plausibility of mechanism, study design and data quality, real-world costs and benefits, novelty of finding, and other factors that vary by research domain, without giving priority to p-values or other purely statistical measures. Thoughtful researchers use a toolbox of statistical techniques and consider multiple approaches for solving problems.
Those are some general, non-technical suggestions, and in case you aren't getting sleepy enough yet this afternoon, here are some sampling of some more technical suggestions that you'll find in the special issue. Along with the standard p-value, null hypothesis, report some pre-specified other hypotheses. For example, instead of assuming no effect, decide in advance the minimum meaningful effect size and put that as your null hypothesis. Compute a p-value based on that. Transform the p-value into the s-value, which is known as the Shannon information, surprisal, or binary logworth. This turns out to have some useful properties, but perhaps its most useful property is that it can't be interpreted, or therefore misinterpreted, as a probability. And here are a few other ideas that are posed in the special issue of TAS as well.
So, being open, of course, referred to open science practices, to being transparent in reporting data, and so forth. But one thing that might be less obvious is openness to the role of expert judgment and to understanding that subjectivity is involved in every statistical analysis. Tony O'Hagan notes in his paper on eliciting expert judgment that there is essentially no aspect of scientific investigation in which judgment is not required. And we think the words on this slide are important for statistics students as well as researchers to understand. Remember that one study is rarely enough. The words, a groundbreaking new study might be loved by news writers, but must be resisted by researchers. Breaking ground is only the first step in building a house. It'll be suitable for habitation only after much more hard work. Lastly, be modest. And here are just a few of the things that authors recommended in their papers. P-values, confidence intervals, and other statistical measures are all uncertain. Encourage others to reproduce your work. And statistical inference is, or should be, just one part of scientific inference.
Thanks for riding along with us on this p-values update. We have just one more topic to cover. You've probably heard about this controversy. This large group of authors, for very good reasons, propose a change from 0.05 to 0.005 as the threshold. They did not argue this as a permanent change, nor as a change for everyone, but rather as a stopgap measure. Soon after this article appeared, another group made an argument, responded to their article, and if you were to click the ... there between Adolphi and Zwan, you'd find out that there's a slightly larger group of authors opposing that idea, arguing for a variety of reasons that a different approach should be taken. Now, I'm not eager to step into the crossfire of 153 authors that I assure you are all smarter than me, but here's an analogy that addresses my concern about the .005 suggestion. This picture here, for me, is a vivid baseball memory. This is a moment in the bottom of the ninth inning of the sixth game of the 1985 World Series, and I apologize in advance to any Cardinals fans in the room. What you're seeing here is George Orta of the Kansas City Royals crossing first base. He hit a high chopper, which was fielded by first baseman Jack Clark and tossed to pitcher Todd Worrell. Umpire Don Deckinger is closely watching this call, which he badly miscalled. Okay, George Orta was out, but Don Deckinger called him safe. The Royals went on to score 2 runs to win that game, and then went on to win the 7th game of the World Series. This was before instant replay, and this particular kind of play at first base is called a bang-bang play. It's very hard for umpires to make because they have to watch the foot of the runner touch first base while they have to also see the ball enter the glove, so they can't do that, and so they have to actually listen for those 2 sounds. Now, long before I ever started worrying about p-values, I had what I consider a simple, elegant solution to solve the problem of these close calls at first base. So follow along with my simple and, in my own modest way, elegant solution for eliminating these close calls. Simply move the bag 3 feet farther down the line. Then even Don Deckinger can see that George Orta is clearly out, right? No problem. He is out, right? So what's the problem with my elegant solution? Well, obviously, he's out on that call, but there'd just be close calls farther down the line, right? So moving the bag 3 feet farther down the line doesn't solve the problem. It just solves that problem, right? And that's what the .05 versus .005 seems like to me, only it seems more like moving the bag all the way down to the right field warning track. So I'm not quite sure that's the way that we should solve the statistical significance issue.
So now we've arrived at the next phase of the process of moving to a world beyond p less than .05. And, frankly, it's really going to be hard. How do we teach this stuff? Well, Ron and I don't have the slightest idea. Our hope is to start a discussion at this conference and other venues that will, over time, lead to the change that's needed. To us, it's obvious that things can't keep being done this way. It's broken. We have to own up to our part of that and fix it. That's it for P-Values Update. I'm Allen Schirm.
And I'm Ron Wasserstein. Apologies to SNL. Have a great conference, everybody.
Thanks very much. We have time for questions. Yes. Speak up, please. Stand up, please.
So I'll repeat the question as best I can. What to do in classes so that, how to teach this when students are going to hear it differently in other classes, and not to be just taught it mindlessly and so on. Is that a good enough summary? Yeah, so there's always the problem of how you teach it in your classes versus what they're going to hear in other classes. And Alan and I didn't come to this conference to represent ourselves as experts on statistics education. All I have to offer here is that teach p-values as continuous measures of evidence and not as something that could or should be dichotomized. I certainly don't have the answer to the question, what do you do when it's being taught differently down the hall? Yeah, please.
One thing, I don't have anything particularly to add to that, but Andy Gelman at Columbia has a wonderful blog post, and this came up at some point. It may have been more than a year ago, and the question was, well, you know, if we're going to abandon statistical significance, should it even be taught? And I don't know that he even read all of the back and forth, but one of the points was you can't really understand the last 90 plus years of statistics without teaching it and going and reading the literature. But I think as Ron says, I think the ASA statement is a valuable tool. It's very concise and it lays down some principles on which there is very broad agreement. Continual reference to that can be helpful.
And I have no doubt that this will be a topic of breakout session 2A here in a little bit.
Good reminder, Ron and Alan will be leading one of the breakout sessions and coming up in half an hour or so. I'm going to take the liberty of asking the next question if I might, and I have the microphone, so I might. What happens to the topic of power? I mean, is not power the probability of rejecting the null hypothesis, which depends on a dichotomized choice? And if one never speaks of rejecting a null hypothesis, how does one speak of power? Should one speak of power?
One should speak of power, but it becomes more complicated now.
Yeah, I sort of view it, the power calculation as a calculation to do something that you shouldn't ultimately be doing, which is a significance test. But, there still is a need to determine sample size. But, that can be based on considerations of what kind, what width of interval estimates do we want to obtain. But yeah, it's the supplement to the ASA statement by Sandra Greenland and several colleagues has some discussions of the misinterpretations of power. But otherwise, most of the focus in these discussions has been on statistical significance. But we all need to keep that in mind. But then really think hard about the real problem of if you're designing an experiment or any other study, how big a sample do you need and how do you allocate it?
Thanks. I have another question. You might dodge this one, but I tell everyone who will listen that the first thing they should read in the special issue is the lead editorial. Do you have advice for what I should say is the second thing they should read?
There's several articles in there that are really worth grabbing. There's an article by Tong that I think has a lot of interesting features because it talks a lot about the importance of design in it. The article about abandoning statistical significance has a lot of layers to it beyond just the title that I think are important to look at.
Yeah, both of those articles, the Tong piece, the one by Blake McShane and colleagues, I think, the title is Abandoning Statistical Significance, and one by Valentin Amrine and David Trofimo and Sandra Greenland. All of those partly just for their breadth of coverage, I think, are very good. Steve Goodman's paper
Yes.
is really good because he gets into the need for institutional change, that it can't be just statisticians working in isolation, but a lot of other things need to be changed, and you need to work very broadly. It can't be just ASA, and get other professional associations involved, get National Academy of Sciences, organizations like that, work across all the disciplines. So that has a little bit of a different perspective that I think is very useful.
Thank you.
Thanks.
Another question? Yes.
The concept of justifying your alpha or type 1 error, because it at least encourages you to consider the cost of making types of errors, whether it's a type 1 error or type 2 error or just choosing one model over another. Can you say something about considering the cost of making an error in this discussion of p-values?
Okay.
The importance of considering the costs of both type 1 and type 2 errors and how to balance them, and is that a fair characterization?
Sure.
Yeah. One of the quotations on one of the slides was actually from the McShane et al. Article on abandoning statistical significance, where they really, they call them the subordinate factors. All these terribly important things that have been subordinate to statistical significance, and one of those is costs and benefits. And they don't elaborate much beyond that. There isn't, when you're asking about other papers, there's a paper by Chuck Mansky and a colleague that actually looks at statistical decision theory. And in a particular applied context. But I mean, that's a formalized way of considering the costs of different courses associated with different, and benefits associated with different courses of action.
Over here.
Hi, I'm Kyle. I teach AP statistics, and my question is, how are we going to get this to be changed in a meaningful time frame? Because right now, statistical significance is one of the cores of the AP statistics curriculum.
You can take that one.
All I'm going to do is repeat the question. How do we get that change in the AP statistics curriculum? And we're not the experts on this at all. I imagine there's lots of people in here who know a whole lot more about that than we do. So that's why we're here, is to start that discussion. We don't know the answers to that at all.
I think that's enough softball questions. Does anyone have a challenging question for Alan and Ron? Ido, go.
Thanks for an inspiring discussion. I think that we need to think not just of how we are going to teach this from now on, but what to do about the resilient people out there who just finished their studies last year or last decade, and all the scientists and the general public, and the people who only took a single introductory statistics class. We need to find a way to communicate these ideas to them about what replaces what they think is an irreplaceable statistic or concept. So there needs to be additional communication, not just to statistics educators, but to the general public, who is the consumers and the users of statistics out there.
So not just to this audience, but to journal editors, to study panels, to researchers. Yeah, this editorial and this special issue is less than 2 months old. So we're just getting started.
One more question, comment? Yes.
My name is Helen. I'm from Seattle, Washington. I teach Mathematica college, and I kind of represent the two-year voice in this. And let's see, we have 300,000 students that are taking introductory stats in the community colleges. That's like an 87%
Okay, so that was, first of all, really good teacher voice projecting there. But so probably most of you heard that, but the opportunity to rethink outcomes, especially for the huge two-year college population. So I am years away from my teaching of the introductory statistics class, but I have the microphone for a minute and just realized that I do. And so I'll just take this opportunity to say that what I remember from those days of teaching to the introductory class in a four-year college is that the sensation of a lot of hand-waving that had to go with trying to teach why confidence intervals and dichotomous p-values made sense when they really don't. And so I think there is the opportunity to undo that. It's just going to be really hard to undo it. And as you pointed out, there's a whole lot of undoing at a whole bunch of levels. And so we know that this is really early in the game, and we also know that it's a hard problem, and we, again, didn't come here with the idea that we knew how to do that, just only with the really strong sense that it needs to be done. And I hope it was clear sort of where the ASA statement stopped and where the editorial and where Ron, Alan, and Nicole started. The ASA statement was a consensus document. It was a place that was reached by a panel of experts over a period of time, and it was agreed upon by the ASA board of directors. Jessica Utz was on it at the time, sitting there in front of the group. Now we're at a place where that's not as fully agreed upon by the statistics community, but I think it's a very important place, a very important discussion that we're having. I don't think you'll see that everyone agrees that it's time to say goodbye to statistical significance, but that's the point where a lot of people are at, and that's certainly the point that we're trying to convey today. And thank you for letting us have that chance to share that with you today.
And I'll stop the questions there. Thanks again to Alan and Ron.